Hello, today we're going to cover College Algebra section 5.5. We are continuing to work with graphs just like last time, but as you can kind of see from the images here, we're going to go through some kind of weird ones. And these have what we call asymptotes. And I know we've heard this word before, I've referenced it before. Asymptotes are the special kind of magical line that prevents us from dividing by zero. Because remember, if we divide by zero, we create a black hole and destroy the universe. So it can't do that. So this tiny invisible dotted line is saving the universe, and it's called the asymptote. So we have both vertical and horizontal asymptotes. Now the vertical asymptotes are the real lifesavers. They're the ones stopping us from destroying the universe. The horizontal asymptotes are just kind of a trend. It just happens to go along these lines. So these are not as specific, they're not as, they don't prevent us from breaking any rules. It's just a trend. So because of that, a horizontal asymptote could be crossed. If you had a horizontal asymptote in a graph like this, it would just eventually kind of level off and then stick around this line. And that's okay, it could be crossed. But the vertical asymptotes, they're the lifesavers. They can never ever be crossed, because if they were, we'd destroy the universe. So they are very easy to find, the vertical asymptotes. Since we're blocking the bottom from turning into a zero, all we have to do is find out what makes the bottom be zero. But the horizontal asymptotes are actually even easier. Since they're just a trend, what we do is we're actually trying to kind of think through how the numbers react as we get larger and larger towards infinity. So the deep down meanings of them involve limits and kind of intense math stuff, but basically it falls down into three cases. Looking at the powers, either the power is bigger on the bottom, the power is bigger on the top, or they have the same highest power on top and bottom. If the power is highest on bottom, then the horizontal asymptote is zero. Done, no question. That's always the case. If the highest power were on top, then there is no horizontal asymptote. It doesn't follow a trend line, it just goes wherever it wants to go. If they happen to be the same, like this case here, where they both have an x to the understood 1, then we take the coefficients. And really, that's what we were doing all three times. But in the other cases, one of the coefficients was a 0. So let's relook at those really quick. So in the first one here, technically I had 0x squareds up here. And 0 divided by 4 is 0. On this one, I technically had 0x squareds down here. And 1 divided by 0, remember, is undefined. Since that was undefined, that meant there was no horizontal asymptote. So there's a difference between 0. That's the number 0. That means it flattened off right along the x-axis where the y was 0. This one means things go up and down. There's no flattening off. And then this one would flatten off along the line equal to 9/5. All of the y values would eventually settle up right around here. Okay, so we're going to look at some examples. And this first example is the most kind of normal, the most typical, the ones that are almost all of the questions will be like. The rest of the examples that I cover are kind of the special cases, so try not to panic, don't think over them too hard. I just go through those special cases so you kind of know what to do in those special circumstances. But like I said, most of the time they're going to be more normal, like this guy right here. So since the horizontal asymptotes are the easiest, let's start off with that. Looking for the horizontal asymptote, I think through those cases. This one has a higher degree on the bottom than the top because he is an x, he doesn't. That's just a constant. So it's just 0. That's it. You're done. No math involved. Horizontal asymptotes involve no math. You don't do any sort of calculation. No math. Okay? So we're done with that one. All done. The vertical asymptotes involve just a little tiny bit of math, but they only need the bottom. So it doesn't matter to us whatsoever what's going on at the top. We just look at the bottom. So I just take the bottom, 3x. Hang on one sec, let me color code this so we can keep everything nice and neat. So we take the 3x plus 5, and we see what would make that equal 0. We don't care about the top at all. We just want to know what would turn the bottom into a 0 because that number is a no-no. We have to throw them out. So we do that just a little bit of algebra. And we see that that would give us the fraction of -5/3. Okay, so that means that fraction of -5/3 is a no-no. Okay, now since these right here are the graph of a line, this is the graph of the horizontal line, this is the graph of the vertical line. They are lines. It's either the trend line or the dotted line saving the universe. They have to have the letter equals. Okay, it's an equation. You can't just put the number. If I just put 5/3, do you mean x is 5/3? Is y 5/3? Is it 5/3, 5/3? There's not enough information. You have to have x equals 5/3, the equation of the vertical line along x equals 5/3, -5/3. So you have to have the whole thing. So the domain that it asks for next is actually the exact same thing. It's the same 5/3, except we have to say that everything else is good except the 5/3. So basically I just say we're good for every single possible x except -5/3. So notice in the vertical asymptote, x was equal because that was the equation of the vertical line. In the domain, x is not equal because we're saying the x's can be anything except this number, which causes the bad thing to happen. So same answer, not equals, equals. All right, so last they ask us to find the intercepts, and we've already talked about this before. We're just looking at them in these kind of weird cases here. So the y-intercept is always the easiest one to find. So we're gonna start with that. I'd like my pin to be the thinner one right here. There we go. Y-intercept is the easier one because remember in the y-intercept, we always have an x of 0. And if x is 0, we just plug that in. So that would just be 3/3 times 0 plus 5. Well, 3 times 0 is 0, plus 5 is 5. That would be 3/5. Okay. So it is the single point 3/5. So that's how we find our y-intercept, by plugging in a 0. Now the x-intercept is just a little bit trickier, but not bad. So the x-intercept, remember it always seems a little bit backwards, but if you think about its point on the graph, it should make sense. We have the y of 0. So that means we're plugging a 0 in for the y, and remember that f of x is the same as y. So if I replace f of x with a 0, and I have 3/3x plus 5, well, just like we learned with those Tylenol troubles, or headache problems, if I had something with a fraction, I can multiply both sides by the denominator. So if I multiplied both sides by a 3x plus 5, what's kind of cool is that over here we have a 0. And 0 times anything is, of course, still 0. So what we end up with is just the top right here. So it's kind of cool because for these problems, we end up with kind of 4 sides. The x-intercept, you end up with just 0 equal to the top because this would happen every time. We'd multiply by the denominator, 0 times anything is 0. So the x-intercept is the top. The y-intercept, when you start plugging in zeros for x's, you always end up with just whatever was in the back. The vertical asymptote, like we talked about, saving the universe, we took whatever was on the bottom and set it to 0. And then the horizontal asymptote, since we were looking for highest powers, generally those are written up in the front. So we kind of take the 4 sides of this big messy fraction thing. So horizontal asymptote, vertical asymptote, y-intercept, x-intercept. So we end up with these 4 things right here. Oh, let me put top for that one. Nope, not top, sorry, front. Front for that one. There. All right, so having that kind of general idea in mind, like I said, most of the problems will be more like this right here. oh, sorry, we didn't really finish the x-intercept. This right here, 0 equals 3, is invalid. You can't solve that. 0, of course, is not equal to 3. So what happens is in this one, there is actually not an x-intercept. And that seems weird, but if you go in and graph it, it makes sense. We had a horizontal asymptote of y equals 0, where it never hit the x-axis, a vertical asymptote of -5/3, where it kind of balanced out. It had that wall back here at -5/3. It had a y-intercept of 3/5, just right there, right below 1. And then no x-intercept because it had that horizontal asymptote right there. So it all fits together. So if you typed this into your graph, being careful to use parentheses around the bottom, you should get a graph just like this that confirms those 4 pieces right there. So let's see if we can distinguish these 4 graphs from their equations by using this information right here. So what I would use to kind of glance through these really quick is the vertical asymptotes. It'd be super easy to spot the vertical asymptotes, because remember that was just where I set the denominator equal to 0. So this one, the denominator set to 0, of course, would equal a -1. This one, the denominator equal to 0, would be equal to a +5. This one, the denominator equal to 0, would give me a -3. And this one, the denominator equal to 0, would be just that, 0. Okay, so let's look through these 4 graphs and see which one has a vertical asymptote at -1, 5, -3, and 0. So sometimes they're a little bit hard to tell, it's kind of spread out, but these numbers are distinct enough that I should be able to spot them. So right here, this one is definitely the 0. There's no way it could be the 5 or -3. Here's -3, definitely not a vertical asymptote. Here's the 5, definitely not a vertical asymptote. So this one would be the graph of D, where the vertical asymptote is x equals 0. This one back here is back at the negative. Is it -1 or -3? Well, let's look. Oh, here's a point at -3, not a wall. So sure enough, here he is with a vertical asymptote of x equals -1, just like graph A. Okay, this one is over here on the positive side. The only one with a positive one was the 5. So this one must be the graph of B with the vertical asymptote x equals 5. So process of elimination, but just to double check, this one should have an asymptote at -3. There he is. So I know it's not the -1 because here's a point right there, not a wall. So vertical asymptote at x equals -3, like graph C. Okay. So another good, quick, easy check. When you're graphing these, it's super easy to forget to put the parentheses around your denominator. So this quick visual check should help you save a bunch of mistakes. Don't get a wrong answer because you typed in too quickly. All right, so these other examples here, like I said, try not to get stressed out by them. We are gonna look at some of the special cases. So this one had kind of a special thing where we had no x-intercept. These others are also going to have something kind of special happen. So buckle in. We start with the same steps. I always like to do that horizontal asymptote first because he's the easiest. This one has the degree highest on bottom again. Y equals 0. Done. No math. The vertical asymptote. We set the denominator equal to 0. So that means the x squared plus x would equal 0. That's a quadratic. We could use our quad if we set our a to 1 and our b to 1, and the constant is 0, because remember, b is the one next to x. This one's missing the constant, not the x. And that means our quad could give us the answer, or we could have factored, that also would have worked, to get the 2 answers of 0 and -1. So we have 2 answers, and that's okay. We have 2 asymptotes. That means that is also the answer for the domain Remember, these were the equations of the line. The domain is the fact that x can be anything except the numbers 0 and -1. Okay. All right. Then the y-intercept was the easier of the two. So let's do him first. That one ended up being the things in the back because we just plugged in a 0 for the x's. But here's why this one was special. I'd get 0 plus 3 over 0 plus 0. So can we divide by 0? No. So that means this right here does not have a y-intercept. Looking at our other answers, that kind of makes sense because right here we had a vertical asymptote at 0. So remember, that blocked it. It was right there. So that means we couldn't have a y-intercept. So it's all fitting together. Okay, and then last, the x-intercept. This one's just a little bit trickier, but not much. Remember that since we multiplied both sides by the denominator and it would always end up with a times 0, we just look at the top, which means I would have that 0 equals the top x plus 3. That would give me an x of -3. So we can graph it, being sure to type it in with parentheses around both the top and the bottom. And you should confirm all these things. You should see those asymptotes on the axis and also back here at -1. You should see it never hitting the y-axis, but it hits the x-axis, so it's just kind of hard to see. It gets really, really flat right here because remember, it does have this horizontal asymptote at 0. So it does cross over. If you do a trace, so where x is -3, you'll see it does just barely touch the x-axis and then just kind of stays right there underneath it. So these, hang on, let me write it in more proper form. So that is true, x is -3, but we want to write it as the point of -3, 0, the x-intercept point. Okay. All right, let's try this one. He looks like a doozy. Don't panic, we got this. Horizontal asymptote, that's the easiest. This one has degrees the same on top and bottom. Remember, this is an understood 1. So 3 over 1 is really just 3. Okay. So the vertical asymptote is going to be the special case in this one. So stick with me here. The vertical asymptote, I set that denominator equal to 0, which means I can do my quad again, which is going to give me the x of -1 and an x of 2. Okay, those are my two vertical asymptotes, no question. We're going to come back to the domain in just a sec. Okay, so I'm leaving it blank right here because this is a special case and we're going to talk about it. The y-intercept, the pen smaller, there we go, is the easier one where we just set the x equal to 0. So we have 0 plus 0 minus 1, and then 0 minus 0 minus 2. Well, minus 1 over minus 2 would be positive 1/2. Okay, the x-intercept is the one where I set the top equal to 0. Okay, so in this case, when I set that top equal to 0, I get to use my quad again. Sorry. Minus 1 equals 0. Okay, so when I use the quad again, I get the answers of -1 and 1/3. Sorry, this pen is being funny on me today. All right, here's the sneaky part about this one. Notice that these two guys match up. Okay, so here's what's happening. Here's why that's a sneaky thing. So on this problem, if you see something like this right here, where it's a big mess over a big mess, if you took the time to factor it, which you could use the factor program, you would see that it was x plus 1 times 3x minus 1 over x minus 2, x plus 1. There's those matching x plus 1s. There was 1 on the bottom and 1 on the top. So as soon as I saw these matching, when I set the bottom to 0 and the top to 0, I know that actually the graph really just looked like 3x minus 1 over x minus 2. He acted completely like this, except at the point specifically -1. At the point -1, he has what we would call a hole, where right there, there's just kind of a tiny, tiny hole where that value specifically is missing. Everything else right around him looks exactly normal, but right there at -1, there's a hole, because I still can't divide by 0, no matter what. Even though it cancels out, that would have made a 0 over 0 scenario, which is still against the rules. So this is the right answer for asymptotes. Wait, no, it's not the right answer for asymptotes. This is the right answer, got them backwards, for the domain. Because no matter what, I cannot use the value of -1 or 2. They're out, they're against the rules. But this one right here is not a vertical asymptote. You can see it from the picture, okay? There's no line there, there's no wall where it shoots up and shoots down around it. It's just a teeny, teeny, tiny little hole, okay? Because there's a hole there, it's not an intercept. So you can see right there, obviously he's not hitting the x-axis there because it's not a good value. It's a hole that divides by 0. It breaks the rules. So the one and only x-intercept is the point 1/3, 0. And the one and only asymptote is right up here at x equals 2. So because of sneaky things like this, which are rare, remember this is a special case, it is a good idea to type this into your graph and just double check those features, just like we talked about. So it takes 2 seconds, you type it in, you say, yep, there is my horizontal asymptote at 3, there's my vertical asymptote at 2, and then you could say, wait, there's not one back here like I expected. There weren't 2 of them like our last example. You could use your trace button to see that there's no value at -1, because when you type your trace -1 enter, the y would actually just be completely blank. It says there's nothing, I can't do it. And then I would help you confirm that it was the special case where it canceled. We still had to restrict the domain. No matter what, we could not divide by 0, but it wasn't an asymptote, it was a hole. Okay, special case. I'm going to draw some lines here because I know there's a lot going on here. All right, so this one over here is the last one of those special cases that we're going to look at. So we're going to start again with our horizontal asymptote. Those are the easiest, we like those the best, there's no math. Looking at it, I see again that it is a smaller degree on top than bottom. Y equals 0, done, no math. Aren't they the best? You should just answer horizontal asymptote questions all day long. The vertical asymptote questions, not too bad. We just set the denominator equal to 0. Okay, and then right away we're going to see why this is a special case. We type that into our quad. There is another 0, a place missing. We have a squared term of 1, but this time remember it's the middle one missing. This one we had an x, this one we have a constant. So the b is 0 and the c is 3. And when you hit that, it's going to tell you that the two zeros are at plus and minus the square root of 3i. Okay, so since it's an I, that means we don't actually have any vertical asymptotes. And if you graph this, it kind of shows there's no weird lines where it shoots up and down. It's this weird looking curve right here. So the vertical asymptotes do not appear. There are none. Since there are no vertical asymptotes, and the only thing that would make the denominator equal 0 is imaginary numbers, the domain of this problem is good. It's all reals. It's negative infinity to infinity. There are no restrictions. No real number could be plugged in and create a denominator of 0. Because remember, when I square a number, that's always positive. And if I have a positive number plus some more, there's no way that would just randomly turn into a 0. So this one is good. That is the special part of this one. So let's move on to the easier y-intercept. The y-intercept, remember we plugged a 0 in for the x's, which just gives me negative 5 over positive 3. Done. And last, the x-intercept was just a teeny bit harder. We set the top equal to 0, but in this case that is pretty easy. I don't need any sort of factoring. I just set x minus 5 equal to 0, which means that the x is 5. Written as a point would be 5, 0. Okay. So the special case of this one was the fact that even though it had a denominator, it didn't have asymptotes because there was no way this denominator would turn into a 0. Okay, so we can compare those to the graph. It's always a good idea to type that in, just kind of double check that you're getting the right thing. And that is the same, the general idea. So these just important features of graphs, even when they get weird. And then we're going to use the idea behind these graphs to find the zeros in the final grand finale of chapter 5.